In the previous episodes, we've been busy building up a basic program counter circuit. It currently consists of a register to store the current instruction address, which we can enable and disable in order to stay at the current address for more than a cycle if we need to. And we've wired up a simple adder circuit that increments the program counter by a few bytes in order to step to the next instruction in the program. The exact number of bytes can be configured to 1, 2, 3, or 4 bytes, which in theory would allow us to support instructions of different byte length. Don't forget to like and subscribe if you want to see this project unfold. So with our CPU, we don't only want to step to the next instruction, but we also want to be able to jump to locations relative to the current address, like going backwards to do a loop or going forward to skip certain parts of the program. And to do this, we can actually use the exact same circuitry as we had over here for the instruction stepping. One input is again going to be the program counter, but the other input is not going to be the step size, but rather a jump offset, which can come from an instruction or somewhere else in the CPU. And that jump offset will be added to the current PC value and then stored as the new PC. And this allows us to do arbitrary relative jumps in the program. So let's build this up and basically duplicate the circuitry we have here on the right to somewhere here on the left where there's space. Time for some more 283s. 1, 2. Let's immediately hook up power and ground for both chips. And for the first adder, we'll tie the carry input to ground. And now to the fun part. We want to have the current state of the PC be one of the inputs to this adder. Pretty much the same as we did on the right side. So let's actually try to bring the PC inputs over to the left side through some additional wires down here, which is going to be a bit cramped, but I think it's going to work. All right, that's the lower side all wired up. Let's move to the upper side. Now the jump offset is going to come from a different part of the CPU. It's not on this board. This might come from the instruction decoder or something else. So for ease of access, I would like to bring the other input over to this side where it's pretty much lined up neatly, so we can have a DuPont style cable connect to it and bring the data in from another part of the CPU. Pretty much the same we did over here. All right, bit of a squeeze, but seems to work. So down here, this is now our input for the relative jump offset. Let me wire this up to some constant value so we can test things out. All right, I'm going to pull bit number 4, so the 5th bit, up high, which is going to be a jump by 16 bytes. And since we're done with the simple instruction stepping over here, let me reuse the LEDs we have hooked up here to look at what the left-hand side, the relative jump adder is producing now. We also need to connect the carry output of the first adder to the carry in of the second adder. All right, let's see if this works. All right, that looks promising. So the PC started out in 0 state, coincidentally. So we're adding a 16, so the 5th bit set to that value, which is exactly what we get here. But now if we step the PC through the individual instructions, the next instruction address calculation over here is just going to step this through individual bytes. So when we hit this, this will count up. But as we can see here on the left, we're also computing the relative jump address based on the current PC. However, as you might notice, the lowest bit seems to be either not connected somewhere or the LED is just broken. So there's a connection here that seems to be kind of not really good. So let me see if I can bend the pins a bit to make it more reliable. That looks much better. So this is one of the downsides of using breadboards for prototyping. Sometimes you just have to deal with these like unreliable contacts which are inherent in these kind of setups here. But this will all be better once we move things to PCBs and we only ever have a few breadboards that could be broken. So we're dealing with a mostly stable circuit that is reliable and a few, fairly unreliable ones that we need to pay special attention to. All right, so with these wires here, we can configure the jump offset that we want to do. So currently it's set to 16, but this can be basically anything we want. Right now it's 0, so the PC is the same as the relative jump target address. But one of the neat things here is that we can actually do 2's complement addition to jump backwards in a sense. So for example, if we want to jump one step back, which would be, so this is now 16, one step back would be address 15, which is the 4 lower bits set. If we want to do this, we can basically configure -1 as a jump offset. -1, 2's complement notation is basically all bits set to 1. So let's try this out. Let's configure the jump offset to be all ones, which is a -1. It seems like the lowest bit here is not hooked up properly. It looks like this connection is kind of unreliable. Much better. So as you can see, I've configured a -1 here at the offset, which is all ones. And adding this to our program counter is effectively subtracting 1. And we can actually jump back more. We can basically say, okay, let's do -2, which is setting the lower bit to 0. And as you can see, this is now 14, which is 2 steps backwards from 16. And by configuring these step sizes here, we can basically jump forwards or backwards in the program as we see fit. In the next episode, I would like to further extend the program counter such that we can pick whether it should do instruction stepping, relative jumps, or absolute jumps through a select signal. Thanks a lot for watching. Like and subscribe if you'd like to see more of this, and see you next time.